points. I'm just kidding. I will. I will begin with a word of prayer. So, dear Father, we thank you for this day. Thank you for these students. Just ask you to bless our work today and just help us to glorify you what we do, Lord. In your name I pray. Amen. So I have begun to try to explain to you guys the way we solve problems with variational calculus. So let me try to give you a short rundown of it. Essentially, and let's just talk about, I'm going to focus on physics here. So we say the Lagrangian L is equal to T minus U. If you like, that's kinetic energy minus potential energy. This Lagrangian is the difference of the kinetic and potential energy for some system of particles with coordinates. Usually people in the abstract will say like QI, let's see here, and generalized velocities, grief, QI dot. Then, so your Lagrangian is a function of your coordinates, your velocities, and possibly time. All right? And then you set up what's called the action, S. It's the integral of the Lagrangian. Over time. And so this is, you know, I guess technically this is the action. And then Hamilton's principle says that, maybe it's not Hamilton's principle, but somebody's principle says that nature tries to minimize the action. All right? So minimizing the action, turns out we can write that in terms of, say, the variation of the action should be 0, and that implies then the Euler-Lagrange equations. And so in particular, those are the following. d dt of partial L partial y sub I dot is equal to partial L partial yi, and that's for I equals to 1, 2, 3, however many coordinates you got to describe your system. And so this is the so-called energy method in classical mechanics. We write down the Lagrangian that describes the system, find the Euler-Lagrange equations, and those take the place of Newton's laws. So instead of thinking about forces, we think directly about energy. Mm-hmm.
Would this also be, like, Newton's physics falls apart at the quantum level, but energy doesn't, so would this also apply to the quantum?
How does this appear in quantum mechanics? I don't know directly how to answer that question. What's that? Ask Dr. Skimortis, yeah. Oh, Brenson, okay, yeah. Perhaps. I know Euler-Lagrange equations describe physics at the classical level. So there is, beyond this, you can talk about the Euler-Lagrange, like the Lagrangian density, and integrate the Lagrangian density over space-time. And then you get corresponding Euler-Lagrange equations for fields, what we call classical fields. And so those classical fields are the backdrop in which we build quantum fields. But to get from the classical fields to the quantum fields, there's a lot of kind of difficult, somewhat physical, somewhat heuristic mathematics, let's say, this process of there's quantization and there's renormalization. And all of these things have to happen before you actually get to honest-to-goodness quantum mechanics. A more responsible question for me to answer for you is like, is there a variational formulation of semi-classical quantum mechanics? Semi-classical quantum mechanics is the Schrodinger's equation. That's not field theory, it's like quantum mechanics for a particle as opposed to a field. And I'm not sure if I know the answer to that right off. Like, what is the variational calculus side of Schrodinger's equation? I'm not sure I know. That's a great question, Grace. I don't have a good answer to it. There's plenty I don't know the answers to. Lots and lots of things I don't know the answer to. Here's an example. I think this one we'll find the answer to. Suppose you've got like a ring, and it's stuck on a nail. All right, and attached to that ring you have a spring. And then attached to that you have a mass. Right? And so the ring is stuck on the nail, but it can rotate all the way around. We're on a plane that's essentially frictionless, all right? And then you take the spring with spring constant K, right? And you let it go and give the thing a swing. What happens? Can you kind of visualize it? I mean, it's kind of complicated, isn't it? Here's a two-dimensional picture of it. My nail. It's my ring. Spring. Mass. And so, I mean, you can kind of see what's going to happen. It's going to go round and round and round the nail, going in and out according to the spring, pulling it in and out, right? What are the equations of motion for such a thing? Can you tell me how to find x and y as functions of time? Let's let x and y be the coordinates of this. Right? And let's assume that the spring is essentially massless, all right? Then how would we, and I'm assuming it's not a string, but it's like a thin, like a very light metal rod or something that, well, how to say this? I don't want to do that. Well, I'm assuming that somehow the spring is constructed so that it stays straight. I'm not letting the spring bend, that much I want to say. That would be more complicated. So if I do this, what's the kinetic energy for the system? That's relatively easy, right? 1/2 m x dot squared plus y dot squared, right? This is 1/2 mv squared. So the speed squared is just x dot squared plus y dot squared, right? ds dt squared is dx dt squared plus dy dt squared. How about the potential energy? It's the spring force, right? So remember 1/2, how did it go? 1/2 k and then x squared, right? That would be for a one-dimensional spring, right? One-dimensional spring, like this, right? So, this is x. F is equal to minus kx, and then that's equal to minus du dx. You recall from physics 231, we found that u was 1/2 kx squared, setting the potential energy of the uncompressed, the equilibrium spring to be the zero potential, right? So if your spring is not confined to just the x dimension, if it can stretch out in the x and y direction, what would the formula be to put here? Yeah, x squared plus y squared should be what we put here. And so there you have it, the Lagrangian L is m over 2 x dot squared plus y dot squared, t minus u, right? So minus k over 2 x squared plus y squared. And now we can find the equations of motion by calculating the Euler-Lagrange equations. What are they? So partial L partial x dot is what? It is m over 2 partial x dot of x dot squared plus y dot squared. How do you partial differentiate with respect to x dot? Just like you think. And oh, plus this over here. Fine, I'll write it out. So here's the kind of funny thing that really bothered me as a student when I took mechanics, and the professor said that x and x dot were independent. X and x dot are independent variables, he said. And I said, but you just said it's x dot. That means the differentiation with respect to time. How can it be independent from x when it's the derivative of x? Isn't that crazy? And yet, that's the Lagrangian formalism, is to suppose that x and x dot are independent variables. The mathematics of that is to say that you're replacing the space that you're given with what's called the jet space. The jet space is a larger space in which x and x dot are actually genuinely independent variables. But that doesn't really matter. I mean, the point is, there is a mathematical justification, and this is just kind of like sloppy notation for that, okay? And it won't get you into trouble as long as you don't ask the wrong question. So just don't ask too many questions. That's what I'm saying. It's kind of like what's a situation where you're told not to ask too many questions? Somebody give me something politically incorrect to inject here? No? Nothing? All right. Disappointing. But there you go. Partial L partial x dot is mx dot. Hey, what is that? What is mx dot? Mass times velocity. Mass times the x velocity is the what? This is momentum, isn't it? Momentum in x direction. Similarly, you can calculate partial L partial y dot is what? My dot. Going through a similar calculation I haven't written down. So what's partial L partial x? We get what? We get I believe we get minus kx, right? And partial L partial y is minus k times y. Because the partial derivative of x dot and y dot with respect to x and y are assumed to be 0. All right, so let's put it all together. Euler-Lagrange equations. What do they give us here? d dt of partial L partial x dot equal to partial L partial x d dt of partial L partial y dot equal to partial L partial y. What does that give us? We get d dt of mx dot equals to minus kx, and d dt of my dot equals to minus k times y. In other words, the equations of motion are mx double dot equal to minus kx and my double dot equals to minus ky. Oh, that's kind of cool. We could actually solve these, right? These are decoupled. They're just a pair of second order constant coefficient ordinary differential equations. These we could actually just rattle off the solution for if we wanted to, right? We're looking at x double dot plus k over m, x equals to 0, and y double dot plus k over m, y equals to 0. The solution to this is x of t is equal to x naught sine of omega t plus a phase angle, and y of t is equal to y naught sine of omega t plus some other phase angle, where omega is what? See, these both have the same characteristic equation. So lambda is what? Lambda is plus or minus I square root of k over m. So my natural frequency here is just omega, yeah? Which is the square root of k over m. Huh. I was not expecting to actually find the equations of motion, but here they are. Now, when I say find the equations of motion, I'm actually saying, See, this is an unfortunate thing. When we say equations of motion in physics, sometimes we're just talking about the differential equations that describe the motion, right? The differential equations which describe the equations of motion are over here. So these are the quote-unquote equations of motion right there. These are the actual, honest to goodness, I mean, this literally describes the motion. That is the honest, I mean, that's the solution to the equations of motion here. Huh. Hey, that's cool. So what does this say? I mean, you can actually analyze it. If your spring starts out on a certain like circle, and you give it a little oscillation, it'll just keep going around in that circle at the same sort of angular rate. And like it's always going to be on a circle of radius what? X naught squared plus y naught squared, right? Is that right? Oh, I think I'm wrong. I assume that they have the same... No. Oh. In order for it to be a circle, what would we need to know about x naught and y naught? For this to be on a circle, what would we need for x naught and y naught? Yeah, I think at least they have to have the same magnitude, something like that. And I should really have like a cosine for one and a sine for the other. I don't know. There's more to do. It's possible it's on a circle, but it's not guaranteed, right? I got too far ahead of myself there. It's not going to be a... Anyway, let me stop. That's not the point here. I mean, you can stop and try to think about what does that actually look like and so forth. That's a deeper question for this particular example. What if we wanted to do the same example, but in polar coordinates? What would that look like? So in polar coordinates, so we have x equals to r cosine theta, y is equal to r sine theta, right? So what's x dot equal to? X dot is equal to r dot cosine theta minus r sine theta, theta dot. And y dot is equal to r dot sine theta plus r cosine theta, theta dot, right? So if you look at x dot squared plus y dot squared, what do you get? So if we just FOIL it out, right, distribute it out, you see what happens is you get cross terms of a +2 and a -2 of the sine, cosine, r dot, theta dot terms. One from the x dot squared, one from the y dot squared, but those cross terms cancel. And you're just left with, like by the Pythagorean identity, r dot squared, and over here, r squared theta dot squared. So there we go. Thus, the speed squared in 2 dimensions, we can either write it as x dot squared plus y dot squared, or we could write it as r dot squared plus r squared theta dot squared. Right. You might recognize this more if I wrote theta dot as omega. In physics 231, we often write omega is equal to theta dot. This is the angular velocity, right? So when I write r theta dot, what is that? That is the tangential component. It's the tangential component to the velocity, yeah? And so what you're really looking at there is that the velocity squared either can be written as the x component squared plus the y component squared, or you could write it as the radial component squared plus the tangential component squared, because r squared theta dot squared is nothing more than omega squared. Well, excuse me, it's nothing more than r squared omega squared, which is the tangential component squared. So anyway, in short, our Lagrangian is instead m over 2 r dot squared plus r squared theta dot squared minus k over 2 what? X squared plus y squared is what in terms of polar coordinates? Just r squared, right? So the Lagrangian for this spring on a nail rotating around problem is really quite pretty. You know, same physical problem, but in polars now, all right? And so in polar coordinates, what are the Euler-Lagrange equations? We have partial L, partial r dot is mr dot. And if you calculate partial L, partial theta dot is mr squared theta dot. What is partial L, partial r dot? That's m times the radial velocity. What is that? That is the radial momentum, right? So partial L, partial r dot is the radial momentum. What's partial L, partial theta dot? Do you guys remember from physics 231? By the way, it is, well, anyway, I should shut up. It's nice that you've had that course here. If I was teaching differential equations other places, it might not be the case. But here, p theta, which I wouldn't usually call p theta, I'd usually call it L. L is equal to m r squared omega, which is I omega in the physics 231 course, right? That L is unfortunate because now it's the Lagrangian, but let's say that the angular momentum would be mr squared omega, which is that, but by the way, that's also partial L, partial theta dot. Because the angular momentum for a point particle is just mr squared. Excuse me, the moment of inertia for a point particle is just mr squared. So that is the angular momentum. This is kind of neat, right? Because the Lagrangian formalism treats Cartesian variables and polar variables on the same footing, same equations, same theoretical construct, right? It's not like, oh, well, this is circular motion, so we need a different kind of Newton's law. No, there's just Euler-Lagrange equations for every possible kind of coordinate system that you can conjure up, yeah. Mm-hmm. Ah, yes, we will get to z coordinates soon. But good question. Oop, almost erased it. So let me just finish punchline here. What does this look? What are the equations of motion then? So so one of the things I'm trying to tell you is one of the things I've asked you in the quiz is to find the generalized momenta for the model. The generalized momentum, by definition, are just partial L, partial the coordinate dot, whatever your system is. So the generalized momentum for like this problem, the abstract problem I stated at the start, partial L, partial Q I dot is the ith generalized momenta. Of course, that will reduce to just ordinary garden variety m times v for a Cartesian coordinate or for a linear coordinate like the radial coordinate. But for an angular coordinate like theta, it will give you angular momentum. I don't know. It gave me chills when I first saw it, but whatever. ddt of partial L partial r dot is equal to partial L partial r, and ddt of partial L partial theta dot is equal to partial L partial theta, or Lagrange equations for this problem. What do those give us? These give us that m r double dot is equal to minus kr by essentially the same calculations I did for the previous problem. And how about the theta one's different though, right? So this gives us ddt of m r squared theta dot is equal to what? What's partial L partial theta? Is there any direct theta dependence to the Lagrangian here? No, there's not. So partial L partial theta is 0. So that means that m r squared theta dot is a conserved quantity. What is the conserved quantity here? What's the physical significance of that? We're saying that the angular momentum is conserved in this problem. Because the force that we're looking at here, right, it's actually a radial force. It's what's called a central force. In a central force problem, angular momentum is conserved. So that's kind of neat. And these I can actually solve, right? So I'm just going to go ahead and solve it. What's the solution here? R equals to, let's say, big R naught, sine of square root of k over mt plus some phase angle, whatever. And that's R as a function of time. And how about this? And we also have the L naught, right, is equal to m r squared theta dot. And so you could solve that for, well, you could try to solve it. So this would give you that theta, d theta dt, is equal to, what is it? L naught over m r naught squared, sine squared, omega t plus delta naught, yeah? And if you could integrate that, then that would give you theta as a function of time, yeah? You can integrate that, can't you? What's the integral of 1 over sine squared? One over sine squared is cosecant squared, the derivative of cotangent is minus cosecant, yeah? So this is nothing more than cotangent minus cotangent omega t plus delta naught, and then plus the initial angle, whatever that is. There you go. Ooh, hey. So you can see is it on a circle? I mean, is the motion circular? It's not strictly circular, but it's like oscillating around a circle of radius r naught, right? And the angular velocity is not constant either, is it? Omega is a rather complicated function of time, as you can see here. It's depending on the cosecant squared. I don't know. I'm kind of disappointed this wasn't a homework problem in my junior level mechanics class. This is not bad. You can actually work it to the end. They always gave us problems we couldn't work till the end. It was very frustrating. You get to the point of setting up the differential equations and you'd be like, ah. That's it. Now, Grace asked me, could we add a third dimension? Now here, I have an easy time imagining a spring on a nail. But can you imagine a way to connect a spring in three-dimensional space at a point in the middle such that it can oscillate in any direction? A modified tether ball? Hey, that's pretty good as long as you avoid the... That's a great answer to that. It's kind of a modified tether ball. But the trouble is there's that stupid pole in the middle, right? So if we could somehow create a technology that allows the pole to like... What we need to do is to hold the spring from the fourth dimension. Right? If we could hold the spring from the fourth dimension and not get in the way of the mass. But let's suppose we could do that for a second. All right? If you could do that, if you could imagine a three-dimensional setup like this, what would it do? We would just add what? I will admit I have a hard time imagining it in my mind's eye how you'd set this up physically, but there you go. That would be the modified Lagrangian. And yeah. Now, in this case, I think spherical coordinates might be nice. So what would the kinetic energy in spherical coordinates look like? I mean, I'm not going to, if we could go through the Cartesian coordinates, but let's not do that. All right, let's jump to sphericals. And let's use physics sphericals, if you don't mind. So physics sphericals are x equals to r cosine phi sine theta, y equals to r sine phi sine theta, z equals to r cosine theta, if I recall correctly. So here, phi is, the role of phi and theta are interchanged from their usual ones for math. And x dot would be like r dot cosine theta sine, rather cosine phi sine theta plus r, well, minus r. Man, I really don't want to do this right now. What's that? No, you're not. I mean, it's something I wanted to get to. I wish I remembered the answer to this, so I didn't actually have to go through this. I mean, it's not bad, but what I'm doing. So that the product rule and the chain rule gives us this, and similarly for y dot, we get this. Oops. This should have been a cosine theta here, guys. Think through it rather than copying mine down. You'll do better. Let me just spot check my oh, I'm an idiot. Derivative of cosine is minus sine. I had it right to start with. Okay. Z dot's a little bit easier. So if you take this and you calculate the speed squared, x dot squared plus y dot squared plus z dot squared, what's the speed squared in 3 dimensions work out to in spherical coordinates? If you focus your attention on the r dot terms, you can see what happens. When you take the squared parts from the x dot and the y dot, you end up with a cosine squared times sine squared plus, oh, come on. Yeah, I get a cosine squared. There's got to be. That's okay. Yes, I was like, this is not making sense to me. I must have an error. All right. So I get cosine squared plus sine squared, which of course collapses down to give me a sine squared theta, and then I got a sine squared theta plus cosine squared theta. Anyway, after the dust settles, the r dot terms just yield a r dot squared, which is nice. When you look at the phi dot terms, the phi dot squared terms, all right, what do those yield? Those two, if we square them, what happens? We get r squared, sine squared phi, sine squared theta, phi dot squared. Then we get r squared. I think I've got another error there somewhere. All right, what's the error? Cosine sine. Which one is the cosine sine? Thank you. I tell you, that's why I told you. Thank you. Now, when we look at the phi dot squared terms, we get something that's nice, namely that the cosine squared plus sine squared and phi becomes 1. Then we just left with r squared, sine squared theta, phi dot squared. And then the theta dot terms, when you add those, square those up, what do we get? So I get the sine squared plus cosine squared drops to 1, and we're just left with an r squared cosine squared theta dot squared from the sum of these two terms. And then we've got an r squared sine squared theta dot squared. So sine squared plus cosine squared theta is 1, and we're just left with r squared theta dot squared. Now, that's actually the answer, but what have I not done is I've not shown you why the other bunch of terms don't matter, right? Because there's also r dot theta dot, r dot phi dot, and theta dot phi dot terms, cross terms. But when you study those, they all cancel out. For example, r dot theta dot, when you square it, you get products of cosine, cosine and phi, sine, cosine, and theta. On the other hand, from this one, you get, likewise, sine, sine, and sine, cosine. So you got cosine, cosine, you got a sine, sine, like that. But then when you look down here, you get a compensating r dot theta dot cross term, which cancels those after a Pythagorean. It's complicated, but they do cancel out. Anyway, long story short, in the kinetic energy in sphericals, physics sphericals, m/2 r dot squared plus r squared sine squared theta phi dot squared plus r squared theta dot squared. There you go. That's the kinetic energy in spherical coordinates. Now, if you wanted them in math sphericals, what would math sphericals look like? You'd have m/2 rho dot squared plus rho squared sine squared phi theta dot squared plus rho squared phi dot squared. As a point of reference. All right, so great. What's the Euler-Lagrange equations for this really crazy example that we came up with here? So let's see here, let's summarize here. So my L is what? It's m over 2 r dot squared plus r squared sine squared theta phi dot squared plus r squared theta dot squared. What's the potential energy? 1/2 k x squared plus y squared plus z squared, which is what? Good grief. R squared, right? If we're using r as the spherical radius. Obviously, I've used r in two different ways here. R over there was the two-dimensional r. This is the three-dimensional r. So context matters, I suppose. Actually, in physics, typically we'll use s for the two-dimensional polar radius. Like s is arc length. I know. Sorry. But anyway, in my current notation, this is minus k over 2 r squared. And now we can calculate the Euler-Lagrange equations. There's three sets of them, one for r, one for theta, one for phi. And what are we going to get? So partial L, partial r dot, d dt of that, right, is equal to partial L, partial r. What's that give us if we do the math? Partial L, partial r dot is, again, m r double dot. And we get that that's equal to minus k times r. So the radial Euler-Lagrange equation is kind of the same as it was in two dimensions. But the angular ones are going to look a little bit different. Like so d dt of partial L, partial, let's do the phi dot first, okay? Partial L, partial phi dot is equal to partial L, partial phi. Now partial L, partial phi, is there any kind of phi dependence to the Lagrangian? I've got a phi dot dependence, but I don't see a phi dependence, right? So partial L, partial phi is 0. What's partial L, partial phi dot equal to? Partial L, partial phi dot, looking at this, so everything here is 0, except for that middle term right here, and that differentiates to give me a 2 phi dot. That 2 cancels the half, and I'm left with m r squared sine squared theta phi dot. And that's equal to 0. So by the way, this is the angular momentum associated with what? With phi. Now here phi is, if I could draw it, phi is sweeping in a horizontal plane, right? And so if this, and this is theta in this setup, so this is r, and this down here is r sine theta. So as your phi is sweeping like this, your arc length along phi is going to be equal to r sine theta rather, d phi. And so like a little change in arc length along the phi coordinate direction with respect to time is going to give you r sine theta d phi dt, for what it's worth. And that's why we got that term in the kinetic energy of r squared sine squared theta phi dot squared. It's exactly this, because we look a little sweeping out along the, just changing the phi. It gives us this relation between that part of the velocity. Anyway, the long story short of this is that this is, again, I omega. It's the angular momentum. It's just that the radius here with respect to phi is r sine theta. See, r sine theta is the distance from the rotational point with respect to the phi rotation. Anyway, d dt of partial L partial theta dot is partial L partial theta. What's that give us? Oh, this is interesting, see, because there is a theta dependence to the Lagrangian, right? See the theta dependence? It's right here. So partial L partial theta will not be 0. And on the other hand, partial L partial theta dot, that's pretty simple. That's m. So what we got is we've got d dt of m r squared theta dot. That's my partial L partial theta dot. It's just coming from this piece. All right. And partial L partial theta, on the other hand, is what? We've got m r squared sine theta cosine theta times phi dot squared. Because the derivative of sine squared theta is 2 sine theta cosine theta. The 2 cancels with the m over 2 to give us that. You could actually solve these. Like, seriously, like, from front to back, solve these, I think. I would integrate, I'd solve the radial equation, because that's just a second order constant coefficient problem. We know how to do that. The solution would be like, just like we saw in the previous one. Then this says that the angular momentum in the phi direction is conserved for this problem, right? So that means that we could say that L phi is just a constant. So since L phi is just a constant, that means that this phi dot squared is actually equal to, I mean, this says that phi dot is equal to some constant L sub phi divided by m r squared sine squared theta, yeah? So you can square that and put it down in here, and that will simplify a little bit, and then maybe you can solve that. I don't know. But anyway, we found the equations of motion for the problem, even if we can't solve it to the end, yeah? So I found my better set of notes. Well, they're better and they're worse. So I'll post these in course content for you guys, but I wanted to show you some of these things. And I say they're better because I have a few more worked examples in them. They're worse because they're just black and white. But it has, among other things, like the derivation of Snell's law. Do you guys know Snell's law? You've heard of it. In Physics 232, which you may or may not have taken, we learned that when light crosses from one medium to another with an index of refraction n1 to an index of refraction n2, right, when the speed of light changes in the media going from one to another, then the light is bent across the interface, right? And the relation is that n1 sine theta 1 is equal to n2 sine theta 2, right? This is why when you look into pools, things seem like they're one place, but they're actually another, you know? Or if you're looking up at the edge of a pool, you can see things that are where you ought not be able to see them because the light bends, you know? You could see. So light bends at a, oh, come on. That's Snell's law. And you can derive Snell's law from variational calculus. Here's the So I'll post this for you guys, but this is why I said that Bristol-Crone problem. Remember I told you that the math was bad? Yeah, it's bad. So here's the mathematics of the Bristol-Crone problem in gory detail. Gosh. Yowzers. Snell's law is not so bad, though. So the derivation of Snell's law is, it says that light will travel the path of, I think, least time. So to get time, we take ds, we integrate ds over v, right? If v is equal to ds dt, oh man, it's really stuck on there. If v is equal to ds dt, then dt is equal to ds over v, right? So to get the path of least time, integrate the arc length over the velocity. Now, I somehow have gotten, maybe it was in a different color that didn't scan or something. This, I much prefer this equation here. This one's wrong. But anyway, I need like a giant sticky note. Oh, but then it'd still project on top of it. Anyway, so there you go. We have to integrate that. And so what is this? This is a problem of variational calculus. We need to minimize that action. So the Lagrangian here is the square root of 1 plus y prime squared over the velocity as a function of x. And so that gives me partial f partial y prime is 0. I mean, partial f partial y prime is that. Partial f partial y is 0. So I get this Euler-Lagrange equation, and then I put in what it is, which is that y prime would be the tangent of theta, and so I get sine theta over cosine theta like that. And what happens here? So let's see here. Oh, so partial f partial y prime was constant with respect to x. And so that being constant ends up allowing me to prove that a constant is n sine theta. And once you know that a constant is n sine theta, that's Snell's law. N1 sine theta 1 equals to n2 sine theta 2. So did you guys derive Snell's law in Physics 232? Oh, yeah. You can derive it through arguments that the frequency has to stay the same from one medium to another. If you think about the frequency being different as a wave goes from one medium to another, it's just crazy. Because if the frequency was different, that would mean that like waves are getting piled up at the interface. So the frequency almost has to be the same because the wave hits it and it goes on, right? If there's some kind of imbalance in frequency, it means that your waves are somehow piling up at the interchange. So the frequency being the same, I think, allows you to derive it just the same. But let's see here, let me go on. So this is another problem I often talk about with students. If you want to define the geodesic, in other words, the path of least length on a cylinder. So the metric, the distance squared infinitesimally, if you like. ds squared is r squared d theta squared plus dz squared. Here, we're on a cylinder, so the radius is fixed at r, like r equals to r. So, yeah. This is the usual r and theta and z, all right? So anyway, I'm trying to minimize ds squared, which means I'm trying to minimize r squared theta dot squared plus z dot squared. So the other Lagrange equations just end up giving us that theta double dot is 0 and z double dot is 0. And so we integrate twice and we find these solutions. What are those? Those are just, they're just exactly what you'd expect. If you wanted to find the, I have to be careful here not to show a person's grade. Let's see here. So here's a cylinder, right? If I wanted to find the geodesic going from one point to another on the cylinder, all right, suppose this point to that point, what I would do is oh, fine, give up. Just draw a straight line from there to there, because that means that the theta and the z are both see, so that line, which is what this means, it's just a line in z and theta. That line is the geodesic on the cylinder, just like that. So if I go flat like this, you could think of this as just being theta and z, or vice versa, and then you curl it up to give the cylinder, like that. So it's relatively easy to find geodesics using just, using the Lagrangian as being just the integral of ds squared. And so you could also do it for a you try to find the great circles on a sphere, right? Using because there's a relation between the kinetic energy and the metric, right? If you just take the kinetic energy and multiply by dt squared, it gives you the metric. So like, I covered it up, but this thing, oops, that thing, I can't quite get to it. With the, oh, I can't remember it. Maybe I got it on the next page. Let me see here. Oh, there it is. So on a sphere, so I said the kinetic energy with respect to spherical coordinates had three pieces, right? The two angular pieces and the, oh, you already had it, thanks. The two angular pieces, and of course also the radial velocity piece, right? But if you're on the sphere, that's where r dot is 0, right? If you have r equals to r, if you're fixed with spherical radius r, then you're not changing that. So the ds squared just has the angular pieces, r squared sine squared theta, d phi squared plus r squared d theta squared. And you can then look at that as the Lagrangian, if you will, of theta, phi dot, theta dot. And the Euler-Lagrange equations, if you could solve those should give you the equations, the parametric equations for the great circles on a sphere, which of course are the geodesics. Now, I usually get stuck on this when I try to do it directly. It actually works out much better if you try to view like either phi or theta as a function of the other. You can do that. Because if you think about being on the sphere, that means you could possibly write the curve as one angle being the graph of another, something like that. And so then the equations end up being simpler. But it's been a few years since I worked through it. So I just worked this out for you guys, but here it is in my notes. I will post this in case you had trouble following me today. So there's the kinetic energy in polar coordinates. This is the kinetic energy in spherical coordinates. There's the kinetic energy in cylindrical three-dimensional coordinates. Let's see here. We talked a little bit about this already.